Okay, here's the second implicit differentiation video, and this one goes over the second example on the slides that I didn't get to in class. If you've looked at the PowerPoint slides that I uploaded to the Canvas website, then you've seen this, but I want to talk through it real quickly here. It's, as you can see, x squared plus x times y cubed plus y squared equals 4. The x squared, the y squared, and the 4 differentiate easily enough. Of the y squared is of particular interest, but I'm going to start with the product in the middle. Remember, product means two things multiplied together. So we interpret the first factor x as our f function. So x is equal to f, and the second as the y cubed as our second function. So g is equal to y cubed. That makes the derivative of f 1, so f prime is 1, and the derivative of g prime is 3y squared y prime. Why is it 3y squared y prime? Because when you have a term that's just y's, or a function that just has y's as its components, then you differentiate it as you normally would if it was an x, and so we use the power rule. We bring the 3 around front, subtract 1 from the 3, and we have 3y squared. But then because it's a y, it's actually we're actually treating it as a function, and so y is the inner function, and technically we're using the chain rule, so we differentiate it, and so that becomes y prime. Now, another way of looking at this is when you see y cubed, y squared, 2y, anything with y in it that you're differentiating, when you're differentiating using implicit differentiation, you differentiate as you normally do, in this case with the power rule, and then just tack a y prime on at the end. So those are the four components, f, f prime, g, and g prime, that we then use with our product rule, f prime g plus f g prime. So f prime is 1, g is y cubed, so that's the first term, plus f, which is x, times g prime, which is 3y squared y prime. And so there are the two terms that we get when we differentiate this product. Now the next step then is to differentiate the x squared, the y squared, and the 4. Well, x squared, just using the power rule, differentiates as 2x. Now y squared, as I said before, we differentiate normally, so it's 2y using the power rule, but then we tack a y prime on to the end. In this term, all I've done is rearrange the factors in the conventional order. You put the coefficients, the numbers first, then the variables are in the order that they appear in the alphabet, with the y prime coming at the end. The y prime is what we want to isolate. That's what we want to solve for. So I subtract the 2x and the y cubed from both sides, because the only terms that we want on this side are terms that have y prime in them. Then in the next step, I factor out the y prime. So what's left behind from this term is 3xy squared, and what's left behind from this term is 2y. And then finally divide both sides of the equation by 3xy squared plus 2y, and that's where you get the negative 2x minus y cubed divided by 3xy squared plus 2y, and that's your y prime. That's your dy dx. Now these are all the solutions to the, and I'm not going to go over all three of them, or all four of them, but these are the solutions to the four classwork exercises that are found on, I believe it's page 51. In the case of number 1 and number 2, we don't have any products. We just have terms that we differentiate by themselves. X squared differentiates 2x. Again, y squared we differentiate normally, and we have 2y, and we tack a y prime on the end. And the 1 differentiates to 0, and so that's how we get to this step, and I think you can follow the rest. For number 2, again, y squared's by itself. We differentiate it normally, 2y, and tack a y prime on at the end, and the right side differentiates normally as well. For 3, we have a product. The first factor is x, so its derivative is 1. The second factor is y, and so its derivative is y prime. And then you arrange those using the product rule. That gives you the left side of the equation. 12 differentiates to 0, and you can follow the rest. And finally, the last uses a product. The first factor is x squared, so that's f. Its derivative 2x. And the second factor is y, so g is equal to y, and g prime is y prime. And then we arrange those using the product rule. F prime g plus f g prime, and the 8, of course, differentiates to 0, and so then you can follow the rest as we solve for y prime. Now, finally, I handed out these exercises in class. And the reason I want to take a look at these excuse me, solutions is because you may or may not remember, but in the book, the product rule is stated with these multiplications in a different order. I don't actually remember what they are, but they're not in this order. This is the order that I've always used, and it's the order that I've seen in many other books, and it's the order that is in your classwork packet. So in the solutions that I typed up, these multiplications are written out in the order that follows the book. But I wanted to use the order that, or I wanted to at least show you why they were in the order that they were. And so for each of these, if there's a product, then I showed you which is the f, which in this case number 3 here is 2x cubed, and what's the g, which is y. And then that makes this the f prime and this the g prime. And following this order, these are the terms. Using the order that's in the book, you get them a little differently, but that's why they're out of order. So I'm going to post this. I'm going to post this document here in a couple of minutes as soon as I upload this video, and that should help you make sense of why when we implicitly differentiate these relations, they're not quite in the same order that you might have thought that they would be in. You'll come up with the same answer, but they're just stated slightly differently. Okay, so that's it for this video, and